Linseman is a professor of biological sciences and associate executive director of the Nobel Institute for Healthy Aging at the University of Denver. Dr. Linseman teaches courses in neuropharmacology and cell signaling and performs research focused on neurodegenerative disorders and neurotrauma. He received his BS in biology and chemistry from the University of Michigan in 1987. He then worked 8 years as a research technician at the Upjohn Company in Kalamazoo, Michigan. He went back to the University of Michigan in 1996 and completed his PhD in pharmacology. He did his postdoctoral training from 2000 to 2005 at the Denver VA Medical Center and received his first independent VA grant in 2006. He held a joint appointment with the VA and the Denver University from 2006 to 2015 and has been full-time on the faculty at Denver University since 2015. His professional affiliations include the Society for Neuroscience and American Society for Biochemistry and Molecular Biology. Dr. Linseman has published 76 times to date, with many more to come based on his scientific curiosity. Dr. Linseman is a highly valued member of our Scientific Advisory Board. Ladies and gentlemen, it gives me great pleasure to welcome Dr. Dan Linseman to our Zoom call today.
Hi, John. Well, thank you very much for that really kind introduction, and I want to thank John for inviting me today, and thank you all for attending. I've been working for quite a few years on oxidative stress and neuronal apoptosis and how those pathways are involved in neurodegeneration and neurotrauma. And so ImmunoCal was an obvious fit for this research. So what I'd like to do today is to take you through some of our published works and then also through some data that is not yet published in an Alzheimer's model so that you can get an idea of the kind of the vast experiences that we've had studying ImmunoCal. So I'm going to share my computer screen here. And hopefully you can all see that. Called model of repetitive mild traumatic brain injury. So this is more like somebody who maybe gets a series of concussions, maybe an athlete that over the course of a couple seasons gets 3 or 4 concussions. So it's a little bit of a different model, but I can tell you we're seeing significant benefits of the ImmunoCal administration in that model as well. The last study that I want to talk about is actually not published yet. We're in the process of writing this up and submitting it for publication. And this is looking in a mouse model of Alzheimer's disease. And so this again is a transgenic mouse that has expresses a human mutant gene. It's called the amyloid precursor protein gene. And this is the Swedish Indiana mutation of this gene. The amyloid precursor protein is responsible for generating the amyloid beta peptide that ultimately forms amyloid plaques or senile plaques in Alzheimer's disease. And this particular form, the Swedish Indiana mutation, leads to a high turnover rate of this amyloid precursor protein into this toxic amyloid beta peptide. So these mice, they actually develop amyloid plaque pathology just like humans that develop Alzheimer's disease. And typically it takes somewhere between 8 to 12 months for these animals to develop this Alzheimer's-like pathology. So what we did is we began giving these animals, these mice, ImmunoCal in their drinking water when they were 3 months old. And we gave that to them until they were 12 months old. And at that point, we analyzed their brains for biochemical, histological changes that are similar to what you would see in Alzheimer's disease in a person. And so let me start with the measure of glutathione in the brain of these animals, because that's really what we're talking about mechanistically here. And so I can just show you the ratio again. This is the ratio of reduced glutathione to oxidized glutathione in the cerebral cortex of these mice. So the non-carrier mice, these are non-transgenic control mice. These are healthy mice. These hemi-untreated mice, these are the transgenic Alzheimer's mice, untreated. And then these are the transgenic Alzheimer's mice that were treated with immunocal. And similar to what we saw in the spinal cord in ALS or in the brain following TBI, in these Alzheimer's mice, you see a dramatic reduction in the reduced to oxidized glutathione ratio in the brains of Alzheimer's mice. But immunocal treatment over that 9-month period of time essentially prevented that and dramatically preserved the glutathione in the brains of these animals. Now, John had mentioned a patent, something that we were looking at with this protein reelin. Reelin, let me explain what that is. It's a protein that's involved in development of the brain. However, once the brain develops, it plays a key role, particularly in a region of the brain known as the entorhinal cortex and the hippocampus, in inducing something called long-term potentiation and synaptic plasticity. These are processes that underlie learning and memory. And so reelin is released by cells in the entorhinal cortex into the hippocampus, where it signals these cells to facilitate learning and memory. Interestingly, one of the first things that happens in Alzheimer's disease is that reelin expression in the entorhinal cortex goes way down, it decreases. And this likely contributes to the loss of cognitive function, the decreased memory formation that we see in Alzheimer's patients. And so if we could preserve reelin expression, that might go a long ways towards a new therapeutic approach for something like dementia. And so in this first panel here, what I want to show you is we're actually doing a process that's called in situ mRNA hybridization. Here we're actually looking at expression of the messenger RNA transcript for reelin, which will tell us which cells are actually making the reelin protein. Later on, I'll show you staining for the reelin protein, but there reelin is kind of everywhere because it's actually a secreted protein, and so it's all over the place. But in these, it's much more discrete expression because these are the cells that are actually making the reelin. What you can see in the healthy mice, so the blue here are the nuclei again, or the chromatin, just showing you all the cells in this region. And the green is stained for the reelin transcript. What you can see is that in the healthy mice, in the entorhinal cortex, there are a lot of cells that express the reelin transcript. However, in the 12-month-old Alzheimer's mice, you can see that essentially the reelin has been depleted from this region of the brain, which is what we see in human Alzheimer's patients. However, those animals that were treated with immunocals show some preservation of reelin expression in the entorhinal cortex, and that's shown here in this graph. And so immunocal is able to actually protect reelin expression in the entorhinal cortex. We also looked at this by a technique called Western blotting, where we're looking at the actual reelin protein. So that's in this top panel. So you can see reelin is expressed in the hippocampus entorhinal cortex of the control mice. It goes down in the Alzheimer's mice, and immunocal again protects the expression of that reelin. We also stained the brains of these mice to look at reelin protein expression. And so here the green stain is reelin. The left panels are the control mice, the middle panels are the Alzheimer's untreated mice, and the right panels are the Alzheimer's mice treated with immunocal. And here we're looking at entorhinal cortex, and here dentate gyrus, which is the region of the hippocampal structure that the entorhinal cortex reelin-expressing neurons deposit their reelin into. And what you can see is that the Alzheimer's mice show marked reductions in reelin expression in comparison to the control mice, but immunocal treatment really preserves this reelin expression. So you can see that here quantitatively, that these reductions in reelin are actually prevented, largely prevented by immunocal treatment. So not only does immunocal preserve glutathione in the brains of these Alzheimer's mice, but it also preserves reelin expression. The last thing I want to show you, because these animals have this mutation in the amyloid precursor protein and make a tremendous amount of the amyloid beta peptide, they actually form amyloid plaques. And we can look at those amyloid plaques using a compound known as amyloglow that sticks to the plaques and makes them light up. And so this green staining in the different regions of the hippocampus, the dentate gyrus, as well as the entorhinal cortex, these are amyloid plaques that have formed in the brains of these 12-month-old Alzheimer's mice. And you can see in the untreated mice, there are a large number of these plaques. In comparison, here's an immunocal treated mouse. There still are a few plaques, but they are much smaller and take up much less area in the regions of the hippocampus. And we quantified this both by the plaque numbers, so the absolute number of amyloid plaques, as well as the plaque load, which is basically the percentage of the area of the hippocampus that is taken up by amyloid plaques. And what you can see essentially in all cases is that immunocal treatment resulted in somewhere between a 50 and 80% reduction in the amyloid plaque load in these animals, which is really a tremendous effect in this model of Alzheimer's disease. So the last thing that I want to mention is that in addition to these studies that we have published and that we're working on publishing now, we've also published a number of review articles and editorials. This one was on using immunocal to preserve glutathione as a novel neuroprotective strategy for the degenerative disorders of the nervous system. We also published this editorial or perspective article on glutathione precursors like immunocal shielding the brain from neurotrauma. And we also had this article that we published on detailing really the effects of immunocal in this mouse model of traumatic brain injury. And I think really to kind of summarize what we've shown is that immunocal, through its ability to provide a precursor for glutathione synthesis, its effects in the brain and spinal cord are to increase resilience of these central nervous system areas to stress and disease mechanisms. So by preserving that glutathione, we can reduce oxidative damage, we can diminish neuroinflammation, we can preserve neurotrophic factors like brain-derived neurotrophic factor. We can also preserve key cognitive proteins like reelin. And so this combination of effects that immunocal has really leads to really a nice potential therapeutic option, as a nutritional supplement for people. So I think I'll stop there.